This is section 5, which focuses on solving equations and inequalities with logarithms and exponentials. What I did to start the section is just copied and pasted a couple of examples that we had in sections 1 and 4 in order to show you how you've already done a number of these problems and just to refresh your memory. So our first example is from section 1, and it is solving 8 to the x equals the square root of 2. Now to complete this problem, what we did is we got a similar base on both sides and then solved for x. This section was before we did logarithms, so you could also approach this section or the problem by changing it to a logarithm and solving that way. However, I still think changing to a base of 2 is a simpler way of completing the problem. Our second example also comes from section 1, and what we found is we have an exponential distributed throughout the problem. So the first step what we did is we factored out the exponential 2 to the x, and then we used the zero product property. So 2 to the x would have to be 0, or 3x plus 3 equals 0 if you're multiplying the 2. And we determined that 2 to the x can never be 0. The only way to get 0 is if you had a base of 0, not 2. Then we took and we solved the second part, and we got x is negative 3/7. Remember, whenever you're solving, you can check your solutions by substituting the values back in. The third example comes from section 4, and it was solving an exponential, but this time they have different bases, and we couldn't get them into a same base. We have 3 and 7. They don't have a base in common. So we took natural log of both sides and used our properties of exponents and solve for x. You could approach this problem by also taking the original problem and changing it to logarithm form from the beginning, and that would work as well. You'll get to the same answer, although I think the simplifying is much more complex that way. So our first example for today is log base 5 of x plus 1 equals 1. So we are solving these. One thing that we could do is change it to exponential form. We can also take 5 and raise it to each side. As long as we do the same thing to both sides, it will work. Log 5 to log 5 of x plus 1 reduces to x plus 1, and subtract 1 and we get x is 4. You can check this by hand or in your head. So 4 plus 1 is 5, log base 5 of 5 is 1, so it does work. I also want to show you how you can look at it graphically. So you're going to graph log base 5 of x plus 1 and 1. So graph each side of the equation, and you're going to look to see where they intersect. In order to graph log base 5 of x plus 1, we have to do a change of base. So you can do like we did here. We took natural log of x plus 1 divided by natural log of 5. You could also equivalently do log of x plus 1 divided by log of 5. And we're going to look at the graph. So we're looking for when our logarithm crosses the line y equals 1. So we're looking for the intersection. One thing you might want to do is change your window, so you're zooming in on those values. So just changing the window. To zoom in and look at those. It's going to take a while to calculate it and graph it over again. You could zoom in even closer if you wanted to. The zoom button would also work. And what we're looking for here is where they're intersecting. And we can see that they're crossing each other when x is 4. Our calculator will calculate that for us as well. If we do second calculate and the intersection, it's going to ask you which line, and at the top they tell you it's y1. You're going to push enter. It should automatically switch to the second line, which it does. The reason why they ask you for each of those is if you had more than 2 equations graphed. And then a guess will just speed up the process, because all the calculator is doing is taking values and substituting them in and seeing where they're the same. So you can either just push enter again. I'm going to put in a guess of 4. I already know the answer is 4 because we solved it out, but you can also look at the graph. So they're intersecting at 4. So they are equivalent when x is 4. So that is another way that you can solve the problems, looking at them graphically. Let's move on to the next example. We have 5 to the 2x minus 3 times 5 to the x minus 4 equals 0. This is what I like to call a hidden quadratic. One way that we can do this is say, well, let's make t equal to 5 to the power of x. Because then we can say 5 to the 2x would become t squared. So we're substituting t in for 5 to the x minus 3t minus 4 equals 0. And then we can factor this one, or quadratic formula if you're not comfortable factoring or if it's unfactorable. But don't stop there, because we don't want to know what t is, we want to know what x is. So what you're going to do then is substitute 5 to the x in for t. So I end up with 5 to the x equals 4, and 5 to the x equals negative 1. If I take 5 to the x equals 4, change it to logarithm form, I get log base 5 of 4, which, if I am looking for a decimal approximation, you could do log of 4 divided by log of 5 using the change of base on your calculator, and you get approximately 0.861. Make sure you pay attention to if they're asking for exact answers or decimal approximations. Oftentimes they'll ask for both. Then looking at 5 to the power of x equals negative 1, if I take a positive times a positive, which is what you're doing when you're raising something to a power, you're multiplying it by itself, you're never going to get a negative number. So our only solution is log base 5 of 4. Again, you can always check your answers by substituting those back into the equation. Next problem, we have a logarithm again. And when you're looking at this problem, hopefully you see that you can use the properties of logs to reduce or change the equation. I see a subtraction sign, and I know that when I am subtracting logarithms and they have the same base, I can divide. So I'm left with log base 2 of x equals log base 2 of 13. I can take both sides and do 2 to a power of, or you can just simply look at the problem and say, well, it's log base 2, that means x must be 13. Whenever you're working with logarithms, you do want to make sure that the answer that you're getting is an extraneous solution. So you can do that by substituting it back in. You can also start out the problem by looking at the domain. So I have log base 2 of x. The domain has to be 0 to infinity, because we can't take logarithms of negative numbers or 0, so it'd be 0 to infinity. And then ask yourself, is 13 inside the domain? Yes. So this one will work. You can equivalently, if you substitute in the numbers, you would also know whether or not the x value is the solution. Now we're into inequalities, and hopefully you remember from your algebra classes that solving inequalities, the process works the same as equations with a few changes, and we'll talk about those as we work through this problem. So if we have 3 minus 5 to the x is less than 1, the first thing we're going to do is subtract 3 from both sides. And then I'm going to multiply or divide, doesn't really matter, both sides by negative 1. And here's one of those little switches when you're dealing with inequalities. Whenever you divide or multiply by a negative, you need to flip the inequality. So this is one of the reasons why I have been changing the way that some of the problems have been done. Usually if it's an equation, you can just change it to logarithm form. However, if I take this equation and change it to logarithm form, I'm not really sure what is the sign of the inequality. However, if I take log base 5 of both sides, it is much clearer which way the inequality would be. So I have x is greater than log base 2 of 5. Again, we can check a problem like this with substituting a value that fits into that, such as log base 5 of 3, for instance, which would give us 3 minus 5 to log base 5 of 3, which is 3 minus 3, which is 0, which is less than 1. So that will work. So again, you can check those. If they want it in interval notation, it would be log 5 of 2 to infinity. You could also find the decimal answer, however, that just takes some more time. So usually decimals are just approximations anyway, so we don't put much emphasis on those unless we're trying to find an exact time, for instance. Our last problem is log base 7 of x minus 6 plus log base 7 of x is greater than 1. Again, I have a logarithm and I see addition, which means I can simplify this to multiplication, which would become x squared minus 6x when I distribute the x. Here's another one. I could change it to exponential form, but then we run into the problem. Where is the inequality? Which way is it greater than? Is it less than? Etc. So if we take both sides and do 7 to the power of each side, I'm left with x squared minus 6x is greater than 7. Now this problem should look familiar from your previous sections. I believe it was in chapter 2. And it is an inequality with a quadratic. So we moved everything to one side and we factored or used quadratic formula to find our key values. So we had 7 and negative 1. And then we took and we made a number line and we checked those answers. Now just to help speed up this process, let's go back to our log 7 of x minus 6 and our log base 7 of x, so from our original problem, and talk about domain, because this is another domain. Whenever you're working with logs, you need to make sure that it's going to fit in the domain. Logarithms, you can't divide or can't do a logarithm of 0 or a negative number. So the first one, its domain is 6 to infinity, and log base 7 of x is 0 to infinity. So we look at the number line. We're going to talk about those, but first of all we want to say, well, which one is more restrictive? 0 to infinity to 6 to infinity. Obviously the 6 to infinity is our more restrictive one. So this is our domain. This is the number 6 here, which means we don't need to even worry about anything over here. It won't work because it's not in the domain. It ends up being a logarithm of a negative or a logarithm of 0. So those aren't in the domain. So looking at that, we're going to check, well, you can say, well, is it between 6 and 7? Is it greater than 7? So you can test the values. So if I substitute 7 7 in, for instance, I end up with log base 7 of 1, which is 0, plus log base 7 of 7, which is 1. So that should say to you 1 isn't greater than 1. This is a boundary 1. So it would be an open circle at 7. How if we put in a number greater than 7, such as 8, log base 7 of 2 plus log base 7 of 8 obviously is going to be larger than. So this section will work. If we wanted to, we could talk about a number between 6 and 7, such as 6.5. So if I do log base 7 of 6.5 minus 6, plus log base 7 of 6.5, I get 0.605, a number less than 1. So our final answer is going to be 7 to infinity. If they had changed their problem to greater than or equal to, that would change to a closed circle at 7, so you'd have a bracket instead.